Alright, hello everyone. Let's go over worksheet number 8. So here for question number 1, it's asking us what is an electrolyte? So an electrolyte is simply a substance that produces ions in an aqueous solution. So we've got ions here that are being produced. And a great example of an electrolyte is something like sodium chloride. So if you put sodium chloride in water, so like table salt, this is something we're all familiar with, we're going to make sodium ions that are aqueous and chloride ions that are also aqueous. And so just to be clear here, so aqueous means that it's dissolved in water. So we've got sodium ions and chloride ions dissolved in water. And because we have made ions as a process of this dissolution, the sodium chloride is an example of an electrolyte. So an example of a non-electrolyte would be something like sugar. Sugar molecules do not dissociate into ions when you put them in solution, so therefore sugar would not be an electrolyte. So if you get something like this that dissociates into its individual ions, that would be an electrolyte. So therefore the answer for number 1 is C. Moving right on to number 2, which of the following is a strong electrolyte? So let's go through these one at a time. So we've got HCN and HF. These two are, you might recall, these two are weak acids. And then we've got hydrobromic acid. This one here is a strong acid. And this one here, this is methanol. This is an alcohol. So now, having established this, I'll give you a second to think about it. Which of these do you think would be the strongest electrolyte? It's probably going to be the strong acid, right? So the weak acids, the reason these are called weak acids is because they weakly dissociate in water. If you put hydrofluoric acid in water, what's going to happen is a little bit of it is going to dissociate, but most of it is still going to remain hydrogen fluoride, HF. If we put hydrobromic acid in water, a large majority of the HBr is going to dissociate. So what do I mean by dissociate? Essentially, I'm saying that, say, for example, here is my hydrogen and here is my bromine. These two are going to split apart in water. So water is going to break that HBr bond. And so a requirement for that is that the HBr bond be weak enough for the water to break it. You get something like this where you got weak acids, for example, like hydrofluoric acid. The HF bond is so strong that it's very difficult for water to pull it apart. So it's going to mostly stay just as HF, and only a small portion of it is going to dissociate into hydrogen ion and fluoride ion. So those are considered weak acids, and therefore they constitute weak electrolytes. But if a large portion of the HBr dissociates into H plus and Br minus, then that's going to constitute a strong acid, and therefore that's going to be a strong electrolyte. So we're going to produce lots and lots of ions when HBr dissolves in water. So therefore, number 2 is also C. For number 3, what we're doing here is we have this chemical equation, and we would like to determine what the complete ionic equation is for this equation. And essentially what we're doing here is we're taking everything that is aqueous, right? Because we know that aqueous things are the things that are going to electrolytically dissociate. So we've got these 3 species that are aqueous, and we're going to separate them into their individual ions. The reason we don't do it for the silver chloride here is because silver chloride is a solid. And solids, what we're indicating with the solid is that it is not going to electrolytically dissociate. It's just going to basically sit as a big lump on the bottom of the beaker and not electrolytically dissociate. So therefore, we can't split the silver and the chlorine into separate into their separate ions, so we just leave silver chloride as the solid that it is. So which of these would work the best? Well, this one here is clearly incorrect because we have not split apart any of the aqueous ions. Okay, so that's not going to be it. Here we did split up the silver nitrate, but we did not split up the barium chloride. Barium chloride is also going to split up into barium 2 plus and 2 chlorides. So that's not going to be right. And how about C? C gets us pretty close. Yep. All of those are good. Oh, what's going on here? Here we have split the silver and the chloride. But remember what we said here, that the silver chloride has to stay together because that does not dissolve in water. So it does not electrolytically dissociate. And here we've split it up into its ions. So C would not work because we are saying that silver chloride electrolytically dissociates, but we know from this that it actually does not. So let's check D. We've got silver nitrate, yep, barium chloride, yep, and barium nitrate, yep. All of those are aqueous from the equation, but the one that is solid remains a solid, and that's the silver chloride. So we got to keep that a solid. So all of our aqueous species are electrolytically dissociated into their individual ions, and then the one species, the silver chloride, that does not electrolytically dissociate remains a solid. So D is the only one that is correct for number 3. Now, bouncing off of D, we are now, for number 4, we're asked to determine what the net ionic equation is. What's the net ionic equation? So in this situation, here's where we want to cancel out what we call our spectator ions. So I'm going to come back to D here, and we're going to go ahead and do this. Our spectator ions are going to be ions that we see on both sides of the equation. So let's see here. We see barium 2 plus right there on both sides. We see nitrates on both sides. And I think that's pretty much it, because we have silver plus and chloride, but we can't cancel them out here because we don't have silver and chloride ions in the products. So when we have canceled out all of our spectator ions, what we're left with is an equation that has silver ions and chloride ions aqueous in solution in the reactants, and solid silver chloride in the products. So with that, we see that the correct answer for number 4 is B. Number 5 gives us a precipitation reaction of barium nitrate and sulfuric acid, and asks us to determine what the net ionic equation is. So let's see here. We've got barium nitrate and sulfuric acid reacting. So anytime you get a precipitation reaction, you're going to get a double displacement reaction. So what we can see here is an example of the complete ionic equation, and that would be B. So we'll just take a look here at this and cancel out all of our spectator ions. So let's see, we've got nitrates, we've got protons, and we are done canceling out spectator ions because here we've got barium 2 plus and sulfate 2 minus, and those are aqueous, and here we've got solid barium sulfate. So that leaves us with C as being the correct answer, because we have barium and sulfate that are aqueous in the reactants, and here we have solid barium sulfate as our product, precipitate. So those are the things that did not cancel. and that would constitute our net ionic equation. Okay, there we go. So the right answer for number 5 is C. Number 6 gives us this reaction here and asks us to classify it as either a redox, an acid-base neutralization, or a precipitation. And what I like to do for determining whether it's a redox reaction is to figure out if the charge or the oxidation state on any of these elements changes from reactants to products. So I see a metal here. We've got copper on both sides, and I think that's a good candidate for something that can have a changing oxidation state. So let's take a look at this. Here we start out with copper, elemental copper, that's always going to have 0 charge. And then we come over here to the products, and the copper has obtained a 2+ charge. So let's think about this for a second. If the oxidation state of the copper has changed, then that means that the number of electrons that the copper has changed. And that would be very characteristic of a redox reaction. So in this situation, copper has given up 2 electrons. It's given up 2 negative charges, which means that now the charge on the copper atoms is 2+. And that would mean that we have oxidized the copper. So the way I like to think about it is sort of like a ladder, where here's 0 charge, and say this would be negative and this would be positive. Here my copper started out at 0 and it went up to 2+. So here I have oxidized. And if my charge, say it went down for something else, like something that could go from 0 to -2, for example, that would be a situation where that species was reduced. So if I'm going from like 0 to -1 to -2 and so on, I think of the numbers as going down, so I'm reducing my charge. Basically what I'm doing is I'm adding on negative charge, because every electron has negative charge, and that's called a reduction. So those are reduction processes. Similarly, if I started up here with copper 2+, if I were to come down to 0, I have done that by adding 2 electrons to the copper, and that would also be considered a reduction. So that's how reduction would work. Anytime something gives up electrons, something else in the reaction must take those electrons up. And similarly, if something's giving up electrons, there has to be something on the other side that takes those electrons up. And so that's why oxidation always is coupled to reduction. And same the other way around, reduction is always coupled to oxidation. And that's why we always call these reactions reduction-oxidation reactions. But since we're lazy and we don't want to say that much of a mouthful, we just call it a redox. So that's the idea behind redox chemistry. And this is a great example of it because our copper has gone from a 0 charge to 2+, and that would be an oxidation. So therefore this reaction here is a redox reaction. Now in number 7, we are given this reaction where we have sulfuric acid and sodium hydroxide reacting to make sodium sulfate and water. And we're asked to determine what kind of a reaction this is. So let's think about these one at a time. So is it a redox? Well, let's pick sodium, for example. Let's take a look at sodium. Sodium here is going to have a 1+ charge. And sodium here is also going to have a 1+ charge. Right? So if you think about it, you got sodium plus and hydroxide minus, and here you have 2 sodium plus 1s combining with 1 sulfate 2 minus, and that makes your sodium sulfate. So in either case, our sodiums have a +1 charge. Has the sodium gained or lost any electrons? No, it hasn't. So therefore, no reduction or oxidation has taken place. Therefore, this reaction is not a redox reaction. Okay, let's try an acid-base neutralization. So this is kind of easy because we have an acid and a base, and we know that when acids and bases combine, they're going to neutralize. So that's pretty much word for word what B says. But more generally, when you have an acid and a base like this combining, what you're going to see is some kind of a salt, and you're also going to see water as a product of the reaction. So the hydrogen comes from the acid, and the OH comes from the base. Okay, so when you have H and OH combining, they're going to make H2O. So that's where the water comes from. So that's kind of a little bit more characteristic of an acid-base reaction. And it's not a precipitation because we don't see a precipitate forming. Sodium sulfate, you can even check on the solubility table, is a very soluble salt, and so therefore we do not form a solid product, and this reaction is therefore not a precipitation. So number 7 would be B. It's an acid-base neutralization. For number 8, we're being asked to determine which of the following are likely not soluble in water. And this is one of those problems where it's easiest done with just referencing a table, except the table that we have given to us does not show lithium. So we can obviously eliminate sodium chloride because we know just from common experience that sodium chloride is soluble in water. But we can also confirm that on the table. But here lithium, for lithium carbonate, lithium is not shown on the table. But a general trend that we do glean from the table is that alkali metals like sodium and potassium and also lithium, when combined with carbonates, are going to be fairly soluble in water. So like sodium carbonate and potassium carbonate, those are going to be pretty soluble. Lithium carbonate might be a little bit less soluble than sodium and potassium carbonates, but it is still going to be soluble a little bit nonetheless. And so then also we have lead sulfate here and calcium sulfide. And calcium sulfide, perhaps surprisingly, is soluble in water, but the only one that is not soluble is lead sulfate. And that we can glean from the table, from the solubility table that we got. And so the correct answer for number 8 is C. And then number 9 says which of the following are likely soluble in water. And this, once again, is something we can get from the table. And what we find is that potassium iodide is very soluble, ammonium sulfide is very soluble, and rubidium phosphate is also very soluble. So these 3 things are soluble in water. Silver bromide is not. Okay, so the answers for number 9 would be B, C, and D. And then lastly, for number 10, which of the following would not form a precipitation in aqueous conditions? So let's go through these a little bit more systematically than we've done in the past. Let's go ahead and demonstrate what double displacement reaction would look like. And let's take a look at D, for example. So we're going to do a double displacement reaction for D because we're going to make a compound that's well known as being a solid. So let me move this for you and let's get going. Lead nitrate, lead 2 nitrate, plus ammonium iodide. Okay, I'm just getting this from here. And now we're going to do the double displacement reaction. So instead of the lead combining with the nitrate, oops, that's supposed to be a 3 and that's supposed to be a 2, my bad. Instead of the lead combining with the nitrate, now the lead is going to come over here and combine with the iodide. So we're going to make lead, iodide, and I'll assign phases here in a second. And now the ammonia is left to combine with the nitrate. So ammonium that's important, ammonium nitrate. And let's make sure we balance our reaction, so there's just going to be a 2 in front of that right there. And so we got 1 lead. Oh, we need 2 iodides. Okay. So let's take a second here and balance this. We have 2 iodides, so we need 2 leads, and that's going to have to be a 2. Now we have 4 nitrates. Oh, I made a mistake here. I forgot that it's lead 2 iodides, so there's going to be 2 iodides right there. Okay, so we got lead and 2 iodides, 2 ammonias, and 2 nitrates. Good, so we have a balanced chemical equation. And now let me just assign my phases. This is going to be our solid, so this is our precipitate, and this is our salt, which is soluble in water. Okay, so now that we have shown an example of a double displacement reaction, we've also demonstrated how the precipitate forms. So how do you know this is a precipitate? Well, this is something that you can look up on a table. You know that lead combining with iodide would make a solid. So the example that we chose here would indeed form a precipitate, so obviously D would not be the right answer because we're asking which would not form a precipitate. But if you did a double displacement reaction for each of these, so you did it for this one, and this one, and this one, the only one that you would find does not have precipitates in its products would be this one, lithium hydroxide and perchloric acid. So let's take a look at that. Let's just go ahead and do this real quick. So we're going to do a double displacement reaction, and the lithium is going to come over here and join up with the perchlorate. And I'll go ahead and assign the phases here in a second. And that leaves the hydroxide to join up with the hydrogen. So I'll just go ahead and show that as water. So let me take a second and include the phases. And then I'll ask you, does this look like some sort of reaction we've seen before? I think it does. This looks like actually an acid-base reaction. Why is that? Because here we've made a salt, and here we've made water. All right, and this is lithium hydroxide, so this would be an Arrhenius base, right? Because we got a hydroxide there, and this would be an Arrhenius acid, because we have a hydrogen right there. So this, in fact, is an acid-base reaction, and we see no solids forming in the products. So therefore, number 10's answer would be A, because this is an example of a reaction where no solids form in the product, so we do not form a precipitant. So we do not form a precipitant, and these are all aqueous, so therefore the answer for number 10 is A. And that was worksheet number 8.